All right, good morning, everybody. So today we will start by considering some of the questions or discussing some of the questions that were sent by some of your classmates in the chat regarding some things for test number 3. So if you still have some questions, just let me know in the chat and I'll try to address them. Because I was looking at section 9.1 and section 9.2 in the textbook. The material is still, the amount of questions or problems that we can solve at this point is not it's not that many. So we can still start with those sections on Monday or answering some of the exercises on that on Monday. So feel free to send some of your questions regarding the test. Otherwise, probably I'll go over the basics of section 9.1 if there are no sufficient questions. All right. Okay, so I'll begin with Arsalan's suggestion. About identifying what method to use in if you're given an integral. Unfortunately, I don't have some questions prepared for that. So, but maybe I can go through these problems from the practice test, and we'll let you know or how I decide how I decide what method to use for this particular integrals. Okay. So let's start with problem 1. I have the integral of 2x cosine 10x dx. I always start by thinking, will u substitution work? Because that's the easiest thing to do, right? For this particular problem, you only have two choices for the u sub. So you can let u to be equal to 2x, which won't work because du will just be 2dx, but you will have a cosine. So you need to express cosine in terms of u, which is not possible in this case, right? It is possible you'll have a cosine u, but you will have u cosine 2u. So still a complicated integral. The other choice is to let u equals cosine 10x, but letting u equals cosine 10x will require a negative sine 10x times 10. Also, if you let u be equal to 10x, du will just be 10 dx, but you have an extra x in the first factor. So u substitution will not work here. I just tried all of the possible u's and it didn't work. Now I look at how the integrand looks like. Now the integrand is a product, 2x times cosine of 10x. So whenever I see a product, the first thing that goes to mind is integration by parts, okay? So my prime candidate here for the method is integration by parts, precisely because it is a product of two functions, right? And let's see if it will really work. Well, the thing is, you need to choose what your u would be and what would be dv. I understand we have considered the abbreviation ILATE before, which is basically the order of preference for the choice of u, right? First inverse trig, then logarithms, algebraic, trigonometric, and then exponentials, right? Or an easier thing to remember is you choose the u to be the function that is easily differentiable, and dv is the function that is easily integrable, right? So in either case, using ILATE or using the latter principle I mentioned, so here you can take u to be equal to 2x and dv is equal to cosine 10x. And so integration by parts will really work because we already we can have a choice for the function u, which can easily be differentiated, and the choice for dv that can easily be integrated. Okay, and an added bonus is that u after a couple of differentiations will be equal to 0, right? Because integration by we will be sure that integration by parts will be terminated if you end up with a u equal to 0. Okay. So that's how I choose this to be solved by integration by parts. The same thing for problem number 2. U substitution will not work. You can try all three options. You can try 12x, ln of 50x, or just 50x. You will still end up with a complicated product. And again, I noticed that this is a product of two functions. The first one is 12x, which is easily differentiable. ln of 50x, which is easily, is it easily integrable? Actually, it is not easily integrable. But if you go to the ILATE acronym, we can choose u to be equal to the logarithmic function. So that's what I'll try to be the u. And then the algebraic function will be my dv, 12x dx. Again, we can easily differentiate this. We can easily integrate this. So integration by parts looks good for this problem, right? So solve this by integration by parts. Okay. Now this is also IBP. Again, it is a product of 10x and e to the 4x following ILATE. Our choice for u would be the algebraic function, and it's fine because it is it will essentially be equal to 0 after a couple of differentiation, and then your dv would be e to the 4x dx, which is easily integrable. But for this integral, you will let u be equal to 4x. Okay, good so far. So basically, that's the criteria when we choose to use integration by parts. Okay, when you have a product, one of which is easily integrable and the other is easily integrable, right? Now for this problem, it seems that you don't have a product because you can think of it as 2 times the integral of r10x. We only have a finite number of choices, right? So u sub won't work. The other is IBP. And then the other ones are powers of trig, which won't apply here because we don't have a power of trig function here. What else? We did trig sub. But remember, trigonometric substitution only works when you have radicals, right? And then we change the variable into trig function so that we get rid of the radical. So it will not work with arctan of x because it's not an expression involving a radical. And then what's the other one? The last one I think is partial fractions. Is this the last one? Yeah, partial fractions, as the name implies we should have a fraction, but here we don't have a fraction. So essentially here you'll use IBP because that's the only plausible thing here. All the others are impossible except for IBP, because for IBP, our only condition is to choose a function u and a function dv, right? But according to the ILATE principle, you have what? We have an inverse trig, which is the priority for the choice for u. So that could work. This could be our u, and then dv is whatever is remaining. So we'll have dx there because that's the only thing that will remain. And after I took this to be my u, so that would be my dv, and then you're good to go. All right. Okay, so that's it. Obviously, this problem is what? Powers of trig, right? I don't know, Arsalan, were you given the formula for the integral of arctan? I guess you were told to memorize certain formulas, probably the integral of ln, the integral of arctan, probably. So that's fine. If you know the formula, just say in your notes in the exam by the formula given in class, right? So that could be a nice thing to do, because unfortunately we TAs do not know everything that happens in the lecture. So whenever grading your exam, if we see integral of arctan and you just plug in the formula, we don't know what happened. For me, I'll be expecting that you'll use integration by parts. So, I mean, I'll expect to see an integration by parts in your test. But if you were given the formula for the integral of arctan in the lecture and you were told you can use it or quote it in the exam, then that's fine. But it would be good if you can put in your test by the formula given in the lecture, this is the integral of arctan, just to let the grader know that that formula was given in class. Just be careful, Herson. you are integrating arctan and you are not differentiating it. So the derivative of arctan is 1 over 1 plus x squared as you wrote, but the integral of arctan is a different thing, right? All right, so okay. This one, problem 3, obviously it's a power of a trig function. Problem 4, still powers of trig. I guess this is the easiest to spot. Because once you see a product of powers of sines and cosines, secants and tangents, and what's the other one? Cosecant and cotangents, then you use powers of trig. This one is trig sub. Because here you have a radical. So whenever you have a radical of either of the following forms, if you have a squared minus x squared, square root of x squared plus a squared, or square root of x squared minus a squared, if you see any of these three forms, probably you can use trigonometric substitution. I say probably because after simplification or after simplifying all those trig functions, you might end up with a difficult integrand. But I guess that's a nice way to simplify this thing. Right? So you will use trig sub to simplify this expression in terms of a trigonometric function. But as you have seen, integrating the simplified integrand in terms of trig functions might require some other methods. You might need to use powers of trig functions. You might need to use integration by parts or a simple u substitution at the middle of your solutions. But the primal step is trig sub whenever you have this kind of integral or integrands, right? Okay, this is another trigonometric substitution. Yeah. Now I find it weird whenever writing something. Maybe because we're now used to typing things. But anyway, so here, I forgot. Let's identify what's the appropriate substitution. So for here, you will let x be equal to 8 sine x, right? So that when you plug this in into here, you will have 64 minus 64 sine squared, which you can write as 64 times cosine squared x. For this one, we'll use the arctan substitution. We'll let x be equal to 3 tangent theta. Yeah, this should be theta. Okay, here we were told that it's trig sub, which is understandable because we have a radical here of the form x squared minus a squared. And then, I think the rest would be partial fractions. The indication that you'll have a partial fraction is you have a polynomial over polynomial, or if you have a complicated expression that can be turned into a polynomial. Let me see if we have that form. Actually, no, we don't have. But say if you have integral of sine squared x plus 2 sine x minus 3 all over sine x plus 4 dx. It's not obvious here that you have a polynomial over polynomial, but the thing is, if you will let, actually, let me throw in a cosine here. If you will let u to be equal to sine x, then du would be cosine x dx. So this expression can be turned as u squared plus 2u minus 3 all over u plus 4 du, which is now a polynomial over polynomial. But before you do partial fractions here, you need to perform the long division, because here we'll have the degree of the numerator is 2, the degree of the denominator is 1. So that means, yeah, you have no choice but to do long division first. Maybe to make it more exciting, let me just throw in a 3 there. So so that indeed partial fraction will be very helpful here. All right. Okay, so is that good? At least we have an overview of the different methods, and you're right. You should be able to identify almost right away what's the method to be used for a particular problem so that you won't waste time. Hopefully that helped and give you some pointers or that will aid you in your preparation for that part of the exam. Okay. Any questions with those general discussion of the methods? Okay. How's your preparation for the exam? Are you feeling good for the exam? Which is kind of a weird question. Nobody nobody feels good during the exam. Oh, that's nice to hear, Muriel. But that's also the thing I hate, memorizing formula. And I guess you know by now I really hate formulas, so I try to veer away from them. And as much as possible, remember things without memorizing them. Okay, let me see. Problem 12. Okay, so oh, by the way, guys, I don't know, maybe nobody noticed last time I made a terrible mistake in my solution last time for that problem when we look at an upper bound for the error. I think using Simpson's or using the trapezoidal rule. Let me go back here. Though I already deleted all the evidence for that, so you cannot. Because if you remember last time, I tried to show off and give you and try to find the error of the smallest n, so that our approximation to this integral would be within 0.001. And remember, whenever doing Simpson's rule, we need to find the derivative, right? Oh, I still haven't deleted this part. I should have deleted this, but anyway. So, okay. So here was my mistake. I don't know if nobody noticed or you're just too shy to call my attention to this. I want to take the derivative. Oh, this is good. If I take the derivative, I'll get this one. But I guess last time we were dealing with a more complicated expression. I guess we did e to the minus x squared, if I'm not mistaken. And then if I took the derivative by simply saying it's negative 2x times e to the minus x squared, which is good. But when I took the second derivative, I just said it's minus 2x quantity squared times e to the minus x squared, which is wrong because I should have used the product rule, right? This guy is a product, so I need to use the product rule. So that will make the computation for the error for the smallest n difficult because we'll have a complicated fourth derivative. And it's not just that, I need to look for an upper bound for n. Okay, so terrible mistake on my part. I'm sorry about that. But I was a bit surprised nobody caught it. Maybe you're just too tired that day to notice things or things. There are a lot of things in your mind. So yeah, I just realized it when I was teaching in my second class. So I deleted all the evidences. So I replaced that problem in the annotated worksheet that I uploaded, and I erased that part of the recording, at least on the version I uploaded in my website. All right. Okay, so let me go. Yeah, that's also what I'm thinking, but yeah. Okay, let me go to Michael's question. Where should I put it? I'll put it in worksheet 12. which is kind of our worksheet for the review. I'm not sure if this is the one uploaded. This is the version for your class. Last edited March 22, 1103. Probably this is the one. Okay. And let's try to answer their questions here. Okay. Let's start off by with the integral. Let me see what's the number here. Number 5. Evaluate the integral of x squared plus 4 over x cubed dx. What's your particular difficulty with this one, Michael? Because I'm looking at the problem. I see a radical. So it screams trigonometric substitution, all right? So the thing here is, okay, u substitution won't work because my prime candidate for the u substitution is x cubed. It will require a 3x squared dx for the du, which I cannot find on the numerator because I have only a radical there. So it really screams trigonometric substitution. And for that, I will let x to be equal to 2 tangent theta. Mm-hmm. Yeah, Muriel, you're right. The thing is, if you encounter something like this in the exam, then it was probably solved before by your professors. So they already knew that trigonometric substitution will work here, because one pitfall of trigonometric substitution is that you might get a very complicated integral here. But because they decided to put this in the exam, then probably the integral would be much easier after the trig sub. So if you find a very complicated trigonometric expression inside the integrand after you do all the substitutions, then you might have done something wrong. And one common mistake is that students forget to also change the dx. That's why when you write x equals your trig function, don't forget to write this right substitute for dx right away so that you won't forget. Muriel, you need to use 2 tangent x for your x, not 2 tangent squared, because this is an x value which will go inside the quadratic function there. So essentially you will have x squared. If you will try x equal to 2 tangent squared, then you will have 4 tangent to the 4th inside the radical. So, and then that will spell some problems for you because you cannot use the Pythagorean identity for that. Okay, so here I'll do the substitution. I can do it slowly. So x squared, we'll replace it by the square of both sides here. So we'll have 4 tangent squared theta plus 4 all over. X cubed will be 2 tangent theta to the 3rd power. And then dx is replaced by 2 secant squared theta d theta. All right. Then let's start working simplifying these trig functions. Well, the reason why you have an extra 2 here in your trig sub is so that you can factor the common scalar in front of the terms inside the radical. So you'll have tangent squared theta plus 1 all over 8 tangent cubed theta times 2 secant squared theta d theta. All right. And then this 4 will go out of the radical as a 2. We'll have 2, then tangent squared theta plus 1 over 8 tangent cubed theta times 2 secant squared theta d theta. Of course, you can skip some of these elementary steps like factoring the constants out and so on. You can proceed directly to having this expression. Well, what can I do here? 2 times 2 is 4 divided by 8, so that's going to be 1/2. I can put that outside of the integral. And then this guy, the radicand, tangent squared theta plus 1 is simply secant squared from the Pythagorean identity. And that's exactly why we chose that trig substitution, because that trig substitution will allow us to get rid of the radical. Because the whole point is that you have a perfect square inside the radical, and that's what we got here. We have secant quantity squared. That square, that power 2 will cancel the radical out. So we'll have 1/2 integral of secant cubed theta over tangent cubed theta d theta. Right? Because you'll have a secant out of this, then you'll have a secant cubed there, d theta. Okay? Did you reach this particular point, Michael? Or do you guys agree that this is the right expression? Yes, exactly. I think that's the next thing to do here, because you need to try to integrate this. Look at the methods that are at our disposal. Well, they have secants and tangents, but I cannot use powers of trig functions because that will be that will require them to be both in the numerator. So the thing here is I need to play with the identities, and probably I can try to write everything in terms of sines and cosines. Because here, one option is when you have the simplified form, you can try u substitution. But if you try u substitution, your prime candidate for u is tangent theta, right? Something from the denominator. But that will require a du equal to secant squared theta, d theta, which looks fine. But after a second look at the numerator, we have a secant cubed. So we can take out 2 of those powers for our secant, for our du, but you will be left with the secant theta alone there, which cannot be written nicely in terms of a tangent. Okay, so that means that u substitution wouldn't work. Okay, so what we'll do is apply trigonometric identities. So secant cubed is 1 over cosine cubed theta, all over this is sine cubed theta over cosine cubed theta d theta. And then, okay, great, Michael, you reach this point. You'll have a 1 over sine cubed theta d theta, because the cosine cubed will cancel each other out, right? Okay, now at this point, we don't have a rule for sine cubed, but Muriel is correct. You can write it as 1/2 integral of secant cubed theta d theta. Sorry, cosecant. Okay, now, were you given the formula for cosecant cubed or not? Because at this point, after this, I'm gonna use integration by parts. I see. Yeah, perhaps you were given the formula for secant cubed, but not for cosecant cube. So for that, you'll need to remember how that formula for secant cube was derived, and that was derived using integration by parts. So we'll have to write it as cosecant theta times cosecant squared theta d theta. Oh, I now understand what's the difficulty with this problem. Okay, and then so here we have a power of cosecant. The powers of cosecants and cotangents follow the same methods for secant and tangents. So if you go back to powers of trigs, we have 2 cases there, sine and cosine, and combination of secant tangent. The methods for secant tangent works perfectly well for cosecant and cotangent. All right, so you can apply the same mechanism for that. So here I'll write, I'll write this as 1 plus cotangent squared theta d theta. So we'll have 1/2 integral of cosecant theta plus cosecant theta cotangent squared theta. Oh, hold on, but will this work? I don't think this will work. I thought I can squeeze out a u substitution here, but it appears I cannot. So because I'm thinking I will let u be equal to cosecant, but that will require a cosecant cotangent, which I don't have. So I guess I should proceed with integration by parts right away. I will take u to be equal to cosecant theta, the one that is easily differentiable, and dv to be the one that is easily integrable. Okay, so du would be negative cosecant theta cotangent theta, and v is equal to negative cotangent theta. Right? So now our integral would be 1/2 uv, so negative cosecant theta cotangent theta, minus integral of v du. We multiply v and du, so we'll get positive cosecant theta cotangent squared theta d theta. All right. And then in this integral here, I can let w be equal to cosecant theta. So dw is what? dw is negative cotangent squared theta d theta, which is fine because I already have that there. So it's going to be 1/2 negative cosecant theta cotangent theta, and then I'll have minus w and then minus dw. Good so far? I love that meme. But hopefully you still follow. And this would be plus integral of w dw. In the past step, you mean our person here? You mean at this particular step? Well, if I let u to be equal to cosecant, I'll have a negative cotangent squared. But what I have here is cosecant squared. You mean in the first solution that I wrote? Because I can write this as cotangent squared. Oh, actually it won't, because this is cosecant. Right? If I will let u to be this, my du should be cotangent squared or negative cotangent squared. And this is a cosecant, right? Even if I write it using Pythagorean, I'm going to have cotangent squared plus 1. But what I have is cotangent squared, not cosecant squared. Yeah, and that's what I'm using here, person, yeah. Hold on, cosecant, I will have cotangent, cosecant. Oh, check that, person. The derivative of cosecant is negative cosecant cotangent. That's why you cannot use it. The derivative of cosecant is negative cosecant cotangent. The derivative of cotangent is, hold on, this is wrong. You already know that it's Friday. This is wrong. The derivative of, sorry about that. The derivative of cosecant is cosecant cotangent. Yeah, it's not cosecant, it's not cotangent squared. Probably that's why, yeah, Herson, you're correct. That's wrong. Okay, so let me see. Okay, going back here, what could be our right substitution here? Let me think a bit here. Yeah, because here I guess. Okay, so what I'm thinking here is you're right. Yeah, that was a big mistake again. So I cannot let u be equal to cosecant because du will be cosecant cotangent. Right, so I guess here I need to go back to this form. Minus cosecant theta times cosecant squared theta minus 1 d theta. I'm getting a cosecant cube again. All right. I used the Pythagorean identity. Oh, d theta should be inside. Now I'm mixing up my derivatives, but good catch, Harrison. Thank you. So here we'll have 1/2 negative cosecant theta, cotangent theta, minus integral of cosecant cube theta d theta plus integral of cosecant theta d theta. Okay, does this look good? So what I did here is to write cotangent squared in terms of cosecant, okay? And then I distributed the cosecant into both terms, but be mindful of the negative sign here in front. So I have two terms here, one a minus cosecant squared cubed and another plus cosecant theta d theta. All right. Now, what do we have? So here's what we have. We have integral of, okay, 1/2 integral of cosecant cube theta, okay, cosecant cube theta, d theta, currently is equal to, we know is equal to this guy. Okay. But what I see here is that this guy can go inside that, right? So essentially we'll have minus 1/2 cosecant theta, cotangent theta, plus, oh sorry, minus 1/2 integral of cosecant cube theta d theta plus the integral, or sorry, minus the integral. Is it a minus or a plus? Oh, it's a plus. Plus 1/2 integral of cosecant theta d theta. Okay, and then what I can do is, oh, this is exactly what we have on the right side, on the left side. So I can transpose this onto here. So I'll have a positive 1/2 on the left instead, and that completes cosecant cube theta d theta. So this would be what? Negative 1/2 cosecant theta, cotangent theta, and then plus 1/2 integral of cosecant theta d theta. Do you guys remember what is the integral of cosecant theta? I guess for that we have a formula. This is ln of the absolute value of what? Let me double check. It is negative cosecant x plus cotangent x plus the arbitrary constant c. Oh yeah, you're right, Harrison, but with a negative sign in front. Yeah, there should be a negative sign in front. Oh, that was a long one. Yes, that's right, because this expression is for cosecant cube, but what are we solving? We are solving for 1/2 the integral of cosecant cubed. So this cosecant cubed, or the integral of cosecant cubed, will be replaced by this. So, but that gets multiplied by the 1/2 in front. So therefore, our final answer, not final answer, but we are nearing that. This guy, I didn't expect this one to be this long, but anyway, is equal to, remember, it is equal to 1/2 cosecant cubed. That's why you need to keep track of your solution. But we already knew what cosecant cube, what the integral of cosecant cube is. This is this guy. Okay, so this would be -1/4 cosecant theta, cotangent theta, minus 1/4 ln of the absolute value of cosecant x plus cotangent x plus c. And then it won't stop here because, sorry, not x, but thetas. Okay, the variables are thetas. We need to go back to x, but to get back to x, remember our substitution was x equals 2 tangent theta. You can say that, oh, from there, x over 2 equals tangent theta. But recall from SOHCAHTOA, tangent is opposite over adjacent. So if you draw a picture of a triangle, say here's the right angle, here's the angle theta. So opposite theta should be x units, right? Because you have this, opposite is x, adjacent to theta should be 2. So we get that. And then the hypotenuse, you can use the Pythagorean theorem to find the hypotenuse. It's going to be 4 plus x squared, which is basically the original integral, the original radicand from the problem. So look, things are looking nice here because we arrive at one of the legs is equal to the original radical. So that's a good indication that you did the substitution correctly. So we'll revert to the original variable. Cosecant. What is cosecant? You'll have -1/4. Let's look at the triangle. Cosecant theta is 1 over sine, right? And 1 over sine would be, sine is opposite over hypotenuse. So it's going to be hypotenuse over opposite. So that would be cosecant. And then cotangent is simply the reciprocal of tangent. So it's going to be 2 over x. So cosecant theta would be 4 plus x squared over x. Cotangent is 2 over x minus 1/4 ln of this guy's. Plus c. And that's our integral. Muriel, I don't think they will give you this long a problem in the exam. Because here, we did a hybrid of the two methods, actually 3 methods. We use trig sub to get rid of the radical, and then we perform trigonometric identities, trigonometric manipulation using identities to simplify the integrand. But after simplifying, we see that we need to do integration by parts, and after integration by parts, we need a U substitute or a W substitution. So yeah, I don't think they will put something this complicated in the exam. That's why you have several problems that they don't want you to answer a long problem with different layers to it. So yeah, but of course it's nice to be ready for anything. So it's a good thing that we tried answering this one. Okay. But I didn't expect that to be this long, really. And oftentimes you might be given, you might be asked to memorize the formula for cosecant cubed and secant cubed. I think somebody mentioned that you were given the formula for secant cubed. I'm not sure, but actually for somebody who doesn't like memorizing, so yeah, like me, I'll do integration by parts like this. Unfortunately, I don't have any idea about the test or how many free response questions will there be. So yeah. Oh yeah, you knew secant cubed, but cosecant cube is often excluded from the list. Okay, let me look at the other one. Oops, number. Oops. This is problem, I guess. The common question between Herson and Michael, problem 6. Yeah, Muriel, yeah, you can find a general formula for the integral of secant to the n. But yeah, because the higher the power of n is, especially if it's odd, then you'll need to do several iterations of integration by parts. Okay, let me see. Michael and Herson sent this common problem. Fortunately, we only have 3 minutes left. But what was the problem here? Can you tell me exactly what was the difficulty that you encountered? My suggestion, Muriel, if your concern is that they will flag you for memorizing a long formula, I guess just put in your exam from a formula from the textbook. I have this formula, so they will know that you know the formula, or at least you're not just copying from some website. So if you'll put some text to it or some context to it, like say some personal sort of personalized message, quotes and quotes, then we wouldn't think that you just copied it from somewhere else. So make it as personal as possible. That's what I'm trying to say. Okay, so for this common problem that was sent, the substitution is 3 sine theta. So dx is 3 cosine theta, d theta. Okay, after the substitution, what did you get? So let me just try to do it quickly. 3 cosine theta d theta over 3 sine theta times 3 cosine theta. Oh, sorry. Why sine? I should use a tangent. Yeah, I should use a tangent. What's with today? I feel totally off, but anyway. So here, 3 secant squared theta. Then this would be 3 tangent theta. And then we'll have 3 secant theta. Okay, I think that's good. And then let's cancel some of the constants. So eventually you'll have a 2/3 outside, and then you'll have a secant theta over tangent theta d theta. Okay, we got the same thing. Now, whenever you got stuck at this point, try to go back to basic. I mean, try to write everything in terms of sines and cosine, because there are no method from section 8 from chapter 8 that tells us how to integrate something of this form. So go back to basic, try to use the identities involving sines and cosines to see if this thing will simplify. And luckily it does. So you'll have 1 over sine theta, d theta, right? Because this can be written as 1 over cosine times cosine over sine. Sines will cancel. And then 1 over sine is nothing more but a cosecant theta d theta. And then we already saw the formula for that, right? So this is minus ln of cosecant theta plus cotangent theta plus the arbitrary constant c. And then you draw your triangle. Remember, we let x be equal to 3 tangent theta. So x over 3 is our tangent theta, which is opposite over adjacent. So this should be x, this should be 3, and this should be 9 plus x squared. And so from there, we learned that cosecant is what? Cosecant is hypotenuse over opposite. So it's going to be 9 plus x squared over x plus cotangent is 3 over x plus the arbitrary constant c. Yeah, that's understandable, Herson, because usually we take for granted the cosecant and cotangents because the methods for them are in parallel to what we do with secants and tangents. So that's, yeah. So as a reminder, take a look at those formulas. If you memorize the formula for secant and for the formula for the integral of tangent, go 2 steps forward and look at the integral for cosecant and cotangent, because you're right, they might throw that in you for the test. But just in case you did not, you can, I guess, you can still find that. Will it be easy? For deriving the formula for cosecant and cotangent. For cosecant, it's not that easy because you need to multiply top and bottom by cosecant x plus cotangent x. But for cotangent and tangent, it's easy. Write it as sine over cosine or cosine over sine. Do the u substitution. But for cosecant, cotangent, for cosecants and secants, it's a little bit tricky because you need to multiply top and bottom by secant x plus tangent x and cosecant x plus cotangent x to get the right u substitution. Okay, guys. Unfortunately, it's already time, and I have another lab at 12. Sorry if I seem to be all over the place today. I don't know what's with today. Probably I don't have enough coffee yet in my system. But hopefully this gives you some idea of how to answer some problems in the test. So yeah, let me know on Monday what happened to the test and how do you feel about it. And then we'll start section chapter 9 by then. All right. Thank you, everyone. Yeah, you're welcome. See you again on Monday, and good luck on the test.